الحضور. ونبدأ الآن في الجلسة الفنية الثالثة تحت عنوان الذكاء الاصطناعي وتأثيره على تحسين كفاءة أداء محطات معالجة المياه، ويديرها الدكتور أحمد معوض مدير شركة نوفا اندستريز.
Ladies and gentlemen, we will now begin the third session entitled Artificial Intelligence, Water Treatment Industry Performance Optimization Impact. It will be moderated by Dr. Ahmed Maawad, Director of Nova Industries.
Dr. Ahmed Maawad has got his PhD in environmental engineering in 1998 from Alberta University, Canada. He got his master's degree from Windsor University in environmental hydraulic 1993. And his bachelor degree from Ain Shams University, Faculty of Engineering. He is a professor at Al-Azhar University in Cairo. He works as a vice chairman of holding company of water and wastewater company. He had joined the HWCC since 2007 and the head of technical support and planning sector, where he had been responsible for providing technical support for subsidization companies in the fields of planning, operation, and maintenance. Dr. Mawad's experience covered different areas, including water and wastewater design and management during his career. He had worked as a consultant engineer in international consulting firms. Dr. Mawad has more than 50 publications in his area of expertise, and he is now the head of the chairman of Nova Industries.
Thank you very much. Well, good evening, gentlemen. I know that this is the last session, and I ask to bear with us the burden of the presentations, but honestly, it's not by far the least. The topic here is, my colleague Amr asked me to be honored to have this session. I was very pleased because there are two items there, or the two keywords, the artificial intelligence and water treatment, and they're both very close to my heart. So I ask to bear with us because, especially when we talk about artificial intelligence, I think artificial intelligence is linked to digitalization, and as been introduced, I was honored, of course, to be the vice chairman before for the holding company. We're trying to force this new introductions for this new topics as digitalization, especially in the area of water and wastewater. So just to move very quickly to the presentation, I'm honored here to have three gentlemen. We'll start with Dr. Hady Habib. Dr. Hady Habib has received his PhD in 2019 at the age of 29 in electrical power engineering from Helwan University. He got his BSc from Helwan University also in 2014. He's currently working as associate professor in the energy engineering program, Faculty of Engineering, Heliopolis University. He's the chairman of IEEE, Industrial Electronics of Egypt chapter. Hady has a guest editor and reviewer in many IEEE technical science, Elsevier, etc. He's also a keynote speaker in many conferences and webinars. He received many research awards, such as Best Second Inter-Chapter Paper from the IEEE, and he got Best PhD Paper Award that integrated renewable energy, sustainable water management. We'll be honored to have a presentation from him titled Artificial Intelligence-Based Hydrogen Wind Water Solution.
Okay, thanks for the introduction, and thanks Dr. Hatem and Engineer Amr for inviting me to speak in this very interesting and well-organized conference. Well, today I'm going to talk about how to combine the energy with water, with artificial intelligence, and with hydrogen. So we are going first to have a brief about the topic, and then we will start talking about this hybrid system, how it will be configured, and then we will discuss with each other the problem definition and what we would like to reach, and we will see somehow some of the results of our research that we published in the IEEE recently, and then we will have concluding remarks of what we did in our research. So we can start with this very beautiful scene, which is the dream of all the people working in the energy sector and in the power sector, when is to have a world working with 100% renewable energy, And the world is dreaming to achieve this by 2050, which is somehow not so far. And in Egypt, if we are going to talk in Egypt in specific, we have plans to reach in 2035 42% from our electricity generation to be from renewable energy. In this scene, you can find that we will going to depend only on renewable energies, mainly the solar energy, the hydropower, the tidals, the wave, and the hydrogen. And let me say that the hydrogen is a big energy player in this scene, and also it's a unique player in its role. And let me, after that, talk about one of the most important topics is the water energy nexus, and it was highly mentioned in the previous session that there is energy to produce water and there is water to produce energy. So for water and energy example, the hydropower, and we in Egypt are leading in that. The hydrogen fuel is considered as one of the WE nexus applications, the floating photovoltaics and the marine energy technologies. And we are going also to use energy for water, like for example, as mentioned a lot, renewable energy for water desalination and renewable energy for getting underground water pumping. Let us somehow focus on the hydrogen, because we are going after that to talk about our microgrid, which is hydrogen will play the most important role in what is the hydrogen cycle, as mentioned in the previous session, so I will not repeat it in details, but in quick, we have PV or wind or a green energy technology, which will operate the electrolyzer, and the electrolyzer by its role will convert the water to hydrogen and to oxygen. And then we have two alternatives, either to use the hydrogen pipes, which is somehow like the natural gas pipes with some of the updates on. And after that, you can convert the hydrogen back to electricity through the fuel cell. And when you get the electricity, you can send it to the grid through grid interconnection, or you can get this electricity through small fuel cells, which is built in buses or electric vehicles. Okay. So this is the microgrid that we tried to invent in our research. We have offshore wind in a sea or a coastal island, but it's connected to the grid. And we have a water desalination station that is going to convert the seawater to fresh water. And then we have an electrolyzer to convert this fresh water to hydrogen. And we are going to employ hydrogen tanks to store the hydrogen as a form of storing energy. And then we are going to convert this hydrogen to electricity through the fuel cell. In this microgrid, we aim not only to produce electricity, but to sell three things: the hydrogen, the water, and the electricity. And we assume that we have 1 gigawatt of offshore wind farm in the area of the Red Sea. And it's also assumed that the maximum water load that we have in this area is 4 million tons. It's somehow assumed number in order to see how our model will work. And then we came to the problem definition. We would like to operate this microgrid with minimum total operation cost and with maximum income that we can get from selling the hydrogen, the water, and the electricity. And this optimization process or this problem is subjected to some of the constraints, such as the power flow constraints. The amount of the energy produced should be equal to the amount of the energy consumed, and also the amount of the energy sold in the form of electricity. The wind generation should be within the upper and the lower limits. We cannot ask the wind turbine to produce more than its installed capacity. This is impossible. And also the amount of water that can be produced from the water desalination unit should be between minimum and maximum. Cannot ask also the water desalination unit to produce more water than its capacity. And also the electrolyzer should be within the border of its capacity and the fuel cell, and also the amount of electricity that we are going to send to the distribution grid should obey the grid codes and the maximum capability of the distribution grid to carry this power. And also the storage tank of the hydrogen cannot carry more than its maximum or thermal capacity. And the objective function, as I mentioned, is to minimize the total operation cost and maximize the income. And here is the equation that we used for the first objective, which is the minimization of the total operation cost. And we have three operators that we are going to operate it and need an operation cost, which are mainly the water desalination unit, the electrolyzer, and the fuel cell. And also we would like to maximize the incomes that are coming to us from selling the hydrogen and the water and the electricity. And here you can find it in F1, which is the first term is about selling the electricity, and the second term is about selling the hydrogen, and the third term is about selling of the water. Since this is a multi-objective optimization process, so we need to set either weighting factors, and here we assumed that both objectives have the same importance with 50% for each, or to work with normalization method, which is somehow new in the artificial intelligence world, which is mainly solving each objective alone. You try to reach, for example, only a minimum total operation cost and see what is the optimal value of this, and you divide it in the equation. And the same you do for the second objective, which is the maximum income. Okay, please. And here we tried to apply a new artificial intelligence optimization technique, and its name is quantitative structure activity relationship, QSAR modeling, and we get it from the people working in the Faculty of Pharmacy in the drug preparation. The main idea of using this is it has three main advantages, which is the overfitting of the data, the domain applicability to the new structure, and the producing of accurate error estimates for each prediction. And then we began to have two main scenarios that we are going to operate our microgrids in summer. And here we take in our consideration the change of the demand in summer hourly from 12 p.m. to 12 a.m., as you can see here. And also in winter, which is the second case study, and we assume that in summer the total demand is 30% more than that of winter because of using of the air conditions and so on. And we have 3 or 4 methods of optimization that we are going to compare between the normalized QSAR optimization and the weighting factor also QSAR optimization, the particle swarm, and the genetic algorithm. And here what we can see as the results of applying our optimization is that the normalized QSAR has a better performance than the weighting factor QSAR or the particle swarm optimization or the genetic optimization. We could achieve almost $600,000 as an income from selling the hydrogen, electricity, and water hourly in a summer day. And we could minimize the operation cost to less than $400,000 hourly through also using the normalized QSAR, which is better than the weighting factor QSAR and the particle swarm and genetic algorithm. And we found that the share, 6-7% of the income that we achieved is coming from selling the hydrogen, more than that of the electricity and the water, because the hydrogen price of the 1 kilogram of hydrogen is more than $7, unlike the low rates of selling the electricity and the water. And also we applied that in a winter day with less demand of electricity by 30%, and we found that we could even achieve more income than the summer days, and it could reach through using the normalized QSAR optimization to almost $750,000 hourly, and we could even reduce the operation cost to less than $300,000 hourly for all the apparatus in our microgrid, and we found that 69% of our income is coming from selling the hydrogen in comparison to 23% of selling the electricity and 7% of selling the water. Please. And then we came to the conclusion is such a microgrid could help us in selling three things: the electricity, the water, and the hydrogen, which could help countries like Egypt highly in the near future, since Egypt is planning to be a hub of energy in the Middle East area. So through using such ideas or such microgrids, we could sell hydrogen, which could for sure help our economic situation to get better than what we have now. And in fact, using the QSAR optimization technique was highly better than using the state-of-the-art techniques like the genetic algorithm and the particle swarm, and could achieve better performance. And the other point is that using the normalization in multi-objective optimization could reach to better performance by 10%, almost than the weighting factor. And we found that selling the hydrogen could achieve much money than selling of the electricity and the water. Thank you very much.
Thank you very much.